All right, your next question asks you to explain why do PEP and 1,3-bisphosphoglycerate have more energy than ATP. All right, now the answer is different in both of these two cases. We'll go through them both individually. So we'll start with phosphoenol pyruvate. All right, it has the structure shown here. Oh, sorry, don't need the hydrogen there. So bear with me here. All right, there we go. Now we got phosphoenol pyruvate drawn correctly. Now, when a phosphoenol pyruvate the phosphate is hydrolyzed off, right, what you end up with is a species that looks like this. Now, this structure right here is an enol group. Now, enol groups are very, very unstable, and they tend to want to tautomerize or convert to what's called the keto form. So the way this would end up happening with electron arrow pushing is we take the negative charge on that oxygen up there, collapse it down, forming a ketone type group, and then we take these electrons from the alkene, push them over to the carbon, and protonate. So the structure would look something like this in the end, which would be the molecule pyruvate. But this tautomerization reaction, moving from the top to the bottom here, has a very negative delta G. It is the enol form on the top here is a very unstable form, whereas the keto form on the bottom is very stable. And so this tautomerization gives phosphoenol pyruvate a lot more energy than ATP. Now, for our next molecule, 1,3-bisphosphoglycerate, I'm only going to show the portion of the molecule that's relevant for this. Right, basically, 1,3-bisphosphoglycerate has a phosphate group attached to the carboxylic acid covalently here. Now, the reason why this is important is, these electrons here on the oxygen, this oxygen right here, you can draw resonance structures with this, but then you end up with a positively charged oxygen. This same oxygen here would end up being positively charged if we did that. So really, these resonance forms for the most part don't exist, or if they do exist, they're in very, very small numbers. Now, when we actually cleave the phosphate off, we are generating now a very, very stable carboxylic acid with very stable resonance forms, basically two equivalent resonance forms. So this increase in resonance here, which is above and beyond the increase in resonance that we see with the ATP when it gets hydrolyzed. This increase in resonance is very, very stable. Basically, we're doing from something that's very unstable, the resonance form I kind of showed you, to something that is very stable in a carboxylate. This to have a very, very negative delta G. So that is it for this question.